This is problem 29.17. This is just a bit of preamble. If you want to read it, you can, but we start here. We have two long parallel wires, each having a mass per unit length of 40 grams per meter. Instead of saying 40 grams per meter all the time, we're going to define this new variable lambda that's saying mass per unit length. Now, they are supported in the horizontal plane by strings of L is equal to 6 centimeters. So here, L is 6 centimeters here and there. When both wires carry the same current I, the wires repel each other so that the angle between the supporting strings, so here theta, is equal to 16 degrees. A says, are the currents in the same direction or opposite direction? Well, if we look at wires with currents going in the same direction, we see this. So the second-hand rule says if you point your thumb in the direction of the current and you wrap around your fingers, like form a fist, we see that your fingers are making kind of like this loop motion. So this is where the magnetic field is coming out and magnetic field is coming in. We do the same thing for a second wire and we get the same thing. It's coming out and going in. You can think of this as being like positive, negative, whatever, it doesn't matter. But essentially because they're opposites, they are going to attract another. So if the current's going the same direction, it's an attractive force. We are told that it is a repulsive force, which means necessarily that the current is in opposite directions. B then says to find the magnitude of the current. To do this, we essentially have to look at all of these different forces that are acting in the system and balance everything out. So here, along the x-axis, we have two things. We have the x component of the tension, and then we also have the magnetic force. The idea is that this current-carrying wire is creating a magnetic field. Because of that magnetic field, this current-carrying wire on the left feels a magnetic force, repelling it. Same thing, but opposite. This current-carrying wire creates a magnetic field at this point here. Because of this magnetic field here, this current-carrying wire experiences a magnetic force, repelling it as well. So what we have here in the x direction is T sine theta over 2, the x component of the tension, is equal to FB over L. The reason why we say over L is because this is a two-dimensional image, but we're trying to symbolize this like three-dimensional thing. So we're saying that, well, really this actually extends, and we do really need to consider that fact because there's current all down here, right? Like the length does also matter. So this is per unit length. We do the same thing with the components in the y direction. So we have FG, here we're gonna have FG over L, is being balanced out by the component of the tension here. So pulling it up, right? That's going to be T cos theta over 2 in this direction. We can combine these two, like so, and we get this equation. Now, what is FB over L? FB, if you remember, is equal to, I'll just write it out. It is L times I cross B. We have divided by L, right? So the L goes away. And then we can also say that, well, we only care about the magnitude because we know the direction of the forces. So we say IB sine of the angle between them. What is the angle between the current and the magnetic field? Well, here we see that it is always 90 degrees. So this current creates a magnetic field that is tangential to it. So 90 degrees here, this is equal to 1. So we get FB over L is equal to I times B. What is B? If you go back to the theory from this chapter, we know that the magnetic field produced by a very simple straight current carrying wire is this, mu naught I divided by 2 pi A, where A is the separation between the wires. The idea again is that this current carrying wire produces a magnetic field here. How far away is that? Well, that distance here is equal to A. What is A? Well, if this here is L, right? So T is the tension, but also is the length L represented here. This is L. This here is L times sine theta over 2, and we need twice that amount to get this distance between them. That is A. So then what we have is, on the bottom, what is Fg over L? Well, it's going to be mass times gravitational acceleration, but really we care about mass per unit distance. So lambda times g. Take these two, plug them in here. This becomes tan of theta over 2. And on the right, we get mu naught I squared over 2 pi a. And I should write that. And then we have times 1 over lambda g. Plug everything in, given the fact that this is a, and we get this. All we do now is isolate for I, because that's what we care about. What is the current for this all to balance out? We do so, plug in all the numbers, and we get I is equal to 67.8 amps. That is the current required to balance out this system like so. C says, if this transmission line were taken to Mars, would the current required to separate the wires by the same angle be larger or smaller than the required on the Earth? Why? Well, what happens on Mars? Gravitational acceleration is less strong. So if the gravitational acceleration is less strong, that means the tension force required to balance it is less strong. If T decreases, well, that necessarily means that FB also decreases, right? Because we still have to balance it out in this direction. So what we say is that a smaller gravitational force would be pulling down on the wires, requiring less magnetic force to raise the wires to the same angle. Therefore, we require less current. If we look here in this equation, if we decrease G, we decrease I. And that is it for this problem.